Welcome everybody to the second part of our data parallelism discussion. Last time I had really fun talking about these algorithms because having these building blocks, these building blocks of algorithms really give up a very, very powerful algorithms overall. And I want to continue today a bit more on that topic. I will introduce a couple more of these building blocks in the beginning. And in the second half of the lecture, I want to discuss two more complicated examples, just to give you some sense of what is possible and what we can do. And I will try to do some performance analysis to convince you that even if it looks like using these building blocks, these data parallel algorithms, might increase the amount of code you have to write, because you have to write more code, you will see that the overall performance might benefit from it, which is what we are after. So just to remind you, we want to talk about our building blocks for data parallel algorithms, which allow us to describe the operation not in terms of a single element, but the operation of a sequence of elements. And I introduced a couple of them: map, reduce, fold, scan last time. Today I will quickly introduce filter, sort, and I'll leave the join and partition and the flatten algorithm to you. Those are fairly straightforward once you get the hang of it. So the main idea of using these sequence-oriented building blocks is that most platforms have implementations for those building blocks available. So you don't have to come up with your own parallelization scheme. You can always rely on existing data parallel algorithm building blocks. NumPy is the best example for that, right? I mean, the Python community is using NumPy all over the place because it allows them to express their thoughts in terms of thinking about the whole array and not just a single element in the array. And NumPy is very well parallelized on many, many platforms, so you gain a lot of performance from doing so. As I said, the key data type we are talking about are sequences, and we will mostly work with vectors in C++, as already mentioned. Other languages have that as well. But the key part here in C++ is that we refer to elements using iterators. And along the way today, I want to introduce you to a special iterator, which is just incredibly useful in the context of combining these data parallel algorithms. And we will see that in a minute. Okay, let's start with very simple operations that are very common and appear over and over again. One is the gather operation, where you have two arrays, the index array and the input array. And the index array contains the indices into the input array that have to be copied to the output. So in general, it's just output of I equals to the index, the ith index from the index array used to refer to a particular element in the input. Very simple operation. The other one is the opposite, the scatter, where you use again an index array, but this time you use the index array to reference the output, where to put things to from a given input. And that allows us to distribute things in a mixed up way to some output. So let's have a look at that a bit more, just in terms of some depicting. So let's assume we have a data sequence with 15 or 16 elements here. We have an index sequence which says I want to have the elements 3, 12, 4, 9, and 9 again, and so on. And this index is used to pick and choose certain elements from the input data sequence to put them into the output sequence to collect the information in a certain ordering in the output sequence. Very simple operation. So let's implement that. I just created a small example where I want to have 8 input elements, 1, 2, 3, 4, 5, and a couple of indices, 6 indices in that case. And I want to create an output array, which I call gathered, that contains the corresponding elements based on the indices in the output. Well, we already talked about transform, and or it's a C name for the name in C++ we use for the math algorithm, which is really, really simple. We go over all the indices in the input and invoke the transformation function for each of those indices and use that to pick the corresponding element from the input, which is then added to the output array. Fairly straightforward. Again, since all these algorithms have parallelization, parallel versions, you can just use the std execution par argument and use it as a first argument to transform, and that will parallelize the data operation for very large arrays. Just fine. So you don't have to rethink, but you can use the same scheme for that. And obviously, in the end, what we get is the corresponding elements from the input that correspond to those indices we specified by the array. The opposite is scatter, where you have a data sequence, which could be shorter, doesn't have to be shorter than the output sequence, and a set of indices. And here the indices specify where a certain element from the input should go to the output. So the something is wrong here with the arrays, but I think you get the idea. We use no, everything's okay. We use the index to refer to the element in the output. So the first element from the input array goes to the index 3, the second element goes to index 0, and so on and so on. So everything's okay on that picture. Okay, how do we implement that? In order to implement that in terms of data, parallel algorithms, I want to introduce a concept which is called zip iterator. You know it from Python, right? Python has zip. So you can just have 2 sequences, and it allows you to iterate over more than 1 sequence at the same time. In C++, the standard doesn't have something like a zip iterator, but I will show you how you can implement one in a very simple way. So a zip iterator allows to iterate over more than 1 sequence at the same time. It is initialized from a list of iterators, 1 for each of the sequences. And when incremented, the zip iterator increments all iterators it is initialized for. When you decrement the zip iterator, it decrements all the iterators. When you compare the zip iterator with another zip iterator, it will just compare the embedded iterators and will return the conjunction of these comparison operations. And last but not least, and that's the most interesting one, when you dereference a zip iterator, it gives you a tuple of the dereference results of the underlying iterators. So it's a very simple way to abstract several sequences and still being able to use all the algorithms we have been talking about and just apply the algorithm to more than 1 sequence at the same time. Obviously, the iteration will stop once the first iterator reaches the end of the sequence. That makes sense. Okay, so let's have a look at that. Just to give you an example, I have 2 sequences, 2 character sequences in this case, but the elements in the sequences don't have to have the same type. I just used both sequences consisting of chars here for simplicity. And now what you can do, you can use the zip construct, and I will show you how that's implemented in a second, by passing the 2 sequences to it and use it in a normal iteration context. And as you can see, each element of that sequence is now a tuple, which we can explode into 2 separate elements by using that C++ So in the end, what you have two sequences, and you zip them into one sequence where the resulting sequence consists of pairs, in this case, of the corresponding elements of the input sequences. As I said, for those who know Python and have worked with zip in Python, nothing surprising. It's really absolutely the same. Just for the curious, how that is implemented, this is the zip function which is being invoked here. And it has to be invoked with at least two ranges, R1 and R2. But I just provided a implementation that can be invoked with arbitrary number of input sequences. There's a typo here, that should be RS. So the last template pack should be RS. And what we do, we create a pair of iterators where the first iterator refers to the beginnings of the given sequences and the second iterator refers to the end of the two given ranges, and combine it with an iterator range, which is nothing more than a pair of iterators. You can think of it as a pair of iterators, which can be used wherever a range is expected. Okay, so let's have a look at the zip iterator implementation itself. For simplicity here, I'm building a zip iterator which can combine two iterators, IT1 and IT2. And obviously it has to store those, right? It will store the two iterators inside. What do we need? Well, we need a way to construct that iterator. That's straightforward, a constructor that takes the two iterators and initializes the two members to the given iterators. Nothing surprising there. We want to be able to compare two iterators, and we have seen how C++ allows you to implement an operator equal. And again, I'm following the same scheme as introduced in one of the first lectures where we talked about types and regular types. And all what comparing two iterators requires is to compare the two embedded iterators. And if both are equal, well, then the two iterators are equal. Otherwise, they will be not. No, nothing surprising. Dereferencing. Well, we want to dereference things, and as I said, when I dereference an iterator, what I want to do, I want to return the tuple that is built of the results of the dereferencing of the embedded iterators. Again, nothing surprising. Increment. Well, increment does two things. It increments both iterators, right? And that's it. Because when I want to move my zip iterator forward, I want to make sure that all iterators it refers to will move one forward with regard to their own sequences. That was a pre-increment. The post-increment is a bit more complicated, and as we discussed, the difference between the pre-increment and post-increment operator, if you want to implement it, is that the post-increment iterator has to have a dummy integer argument, which is never used, which is just used to distinguish these two operators. And what we need to do, we need to take the current copy, then we need to integrate it, increment it, and then we need to return the copy we took before incrementing, pre-increment. By the way, this is a good example where you see why writing ++ iterator might be more efficient than writing iterator ++. ++ iterator is semantically the same as writing iterator ++ if you don't use the results for anything. But the first might be more performant than the second one. And in the implementation, you see very nicely why. Because the post-increment requires you to take a copy, which is not required for the pre-increment version. And again, that's the reason why C++ programmers usually always use pre-increment for their loops. So you will always see something like this. For iterator equals begin, iterator not equal end, ++ iterator. you will never see anybody writing Iterator++. Again, a tip for your programming interview: if it's about C++, just write it this way, and people will just say, "Okay, yeah." They might even ask you, "Why do you use pre-increment instead of post-increment?" You can explain it, yeah, because it's a good habit, because pre-increment might be more efficient than the post-increment. For these simple things, for simple iterators, there's probably no performance difference because the compiler can see through all of that and will optimize it away. But it's still a good habit because you don't know what kind of iterators you're dealing with. You might deal with some very complicated iterators that require you to do, they're very costly to copy. And then the performance difference might be actually measurable. That's it. So there's your zip iterator. So now we can use the zip iterator, combine it with the zip function I give here, right? I'm constructing the zip iterator twice, once for the begins and once for the ends. And from that point on, I will just use the zip function here in all examples on the next slides, and you will know what it's doing. Any questions about that? Oh, good. So let's have a look at how can we implement scatter. How would you implement scatter in data parallel? How would you do that? Well, it's fairly straightforward if you think about it. Because what we need to iterate over two sequences, over the indices and the elements at the same time. That's why I introduced that zip structure, that zip construct. And what our lambda will receive is the tuple that refers to the corresponding elements from the indices and the input sequence, which gives us an integer and a double in this case, because the indices is an integer vector, the elements is a double vector. And then we can just assign the element from the input to the corresponding element from the output by referring to the parts of our tuple. And the way to refer to the parts of the tuple is to use that syntax. Say get 0, note this is a template, which will extract the first element from the tuple, and then will extract the second element from the tuple. And we get exactly what we want. So as you see, zip is a very useful facility which allows us to do these a bit more complicated constructs, but it still allows us to use the very same algorithms we are used to. We don't have to come up with new algorithms that now suddenly iterate over more than one sequence at the same time. Well, this is the expected result. And since I initialized my elements in the scattered out array to 0, you see that we had 4 indices in the input. Now 4 elements in the output are being initialized with the values from the inputs. Fairly straightforward stuff.
I have a question. What happens with the end iterator?
What happens with the end iterator? What do you mean?
Well, when we have a range, it's defined by a begin iterator and an end iterator.
Oh.
And the way we set up the quality function in the zip iterator, it will compare with both of the things that we are.
No, it will compare the begin with the begin or the end with the end, because each iterator contains either the begins or the ends. Let's go back. This is one zip iterator, which refers to one pair of iterators, which is not the begin and end. That's 2 iterators that kind of refer to the same relative position inside the sequences. In the beginning, it's the begin iterators of our sequences. And this is another iterator which might refer to the end iterators.
Oh, but if they do underlying, let's say, vectors that we are zipping through are different sizes, we can just tell it to.
Well, then this equality will not be holding. As long as the first one might reach its end iterator, but the second one will not have reached this end iterator. That means we have reached the end of the sequence. Oh, because not both are true. One is true, the other one is false. So the equality will give you false, which should end the sequence. At least that's the intent.
Shouldn't the equality, shouldn't we have the iterator be
Should be
equal
or
to
given.
an iterator to finish the sequence?
Okay, I might have gotten the logic wrong, but I tend to, with Boolean expressions, I tend to do wrong things. So please figure it out. But you understand what I mean. Okay, I might have gotten it wrong from this right here. Yeah, makes sense. But this is kind of the thing you want to achieve, right? You want to make sure that if one of the embedded iterators is not equal, no. Iteration works this way. You say, while first is not equal to end, plus plus first, and plus plus end, and do something with it. Yeah? Right? And this comparison is in non-equality.
Why plus plus n? Sorry.
Well, we want to go through some sequence. We want to copy. We say star f, sorry, destination plus plus equals star first plus plus for a normal copy. Copy from first to end to destination. Yeah? The while loop will go as long as these two things are not equal. But this is an equality operation. So it's the opposite of what you're looking for. So as long as this one returns true, the loop will go on. Not the opposite. As long as this one returns false, the loop will go forward. As long as the things are not equal, it will increment, because this is not equal. So it's correct on this one.
So we have to choose an end iterator that will eventually be equal. As we increment the other iterator,
yeah,
it has to eventually be equal to.
Well, that's always the case, right? When you give it a pair of iterators, you assume that by incrementing the begin iterator, you eventually will end up at the end iterator. Otherwise, the whole scheme will not work. Right? Okay. Other questions about that? Does it make sense? Or did I get it wrong again? I think I got it right on this slide. Thank you. Okay, I think it's correct. I did not provide the non-equal operator here just for brevity, but we know how that is. It's just a negation of the equality. Okay. So in other words, the iteration over the pair of iterators which is hidden behind the zip will end whenever the first of the sequences is exhausted. Right? Just as a side note, many machines have instructions, assembly instructions, that allow us to perform scatter and gather operations of up to a certain size with one instruction. For instance, there are SIMD instructions on x86 that allow us to gather data items from the memory given an index vector. So by loading the data from the memory, we can determine in what sequence these elements are being loaded into the SIMD register in the core. AVX 512 has these gather and scatter SIMD instructions. GPUs have these operations implemented as well. So whenever you need that, you can rely on the hardware to perform these operations very, very efficiently, at least up to a certain size of the sequences, usually limited by the size of the registers we load things into or we store things through. That's gather and scatter. A very commonly used sequence operation is sort. And there's not much to talk about because it's kind of obvious what it's doing. You provide a ordering criteria, which is a function that takes two arguments and compares two arguments in the two arguments and returns true if the first argument is by default less than the second argument. And the sort algorithm itself uses that comparison function to decide how to reorder the input sequence during sorting. The only notable thing that you might want to be aware of is that C++ at least has two types of sort, just called sort and stable sort. And the difference between sort and stable sort is that stable sort leaves, if there are several elements with the same value, they will not be reordered. So the sequence of elements stays stable when the value of the element is the same. Sort doesn't guarantee that. So for sort, it might happen that the elements get reordered even if the value itself is the same. Now you might say, hey, what's the difference? If I'm ordering a sequence of integers, why do I want to use stable sort instead of sort? Well, for a sequence of integers, it doesn't matter, obviously, because you don't care whether two integers got swapped if the value is the same. But if you're sorting over a zip iterator, where you have two sequences, and you sort based on one of those sequences, then you might want to retain the ordering. Let's say you have a list of employee records where it has a name and the salary. And you want to first sort based on the name, and then you want to sort based on the salary. And the second sort shouldn't mess up the ordering of the names. And that's why you want to use stable sort in those cases, just to avoid that the names get scrambled up just when you start sorting based on the salaries. Okay? There's obviously parallel sort. In this case, it's a non-stable one, but there's a stable sort as well. So you can use the parallel algorithms just fine. The parallel versions usually rely on some quicksort implementation combined with other sorting algorithms underneath. So they are fairly efficient. One interesting application is if all your indices are unique and you want to, let's say, scatter using that unique index. So you have some index which is unique and you have some input data that you want to read things from. In order to get a scattered output, all you have to do, you sort these two sequences together by the index. So if you make sure that the index is sorted, that will flip the corresponding values in an appropriate way, and the output will be a scatter operation. So just as an alternative way to implement things, if you have a very large sequence and you know that your indices are unique, then this operation, implementing it this way, might actually be more efficient than doing the explicit scatter operation by hand. Just as an example, how do we do that? Well, in this case, I just assume that the output needs to be explicitly created, so I copy it, and then I zip over the index and the output, which induce the binary function I'm passing in. The comparison function will receive the reference to two elements of my input sequence, which in both cases will be tuples of something. So I'm comparing based on the indices, which is the first element of my tuple, because zip was constructed from the index as the first argument. This will sort both sequences, but will use the less than function or the comparison only based on the indices. So they will be reordered only based on the indices. Right? That might be even faster than the naive implementation because of spatial locality. So again, and we will see that over and over again, there are many, many ways to implement things. And several of these operations you can do this way or that way. But whenever you're in doubt and you don't know which of those versions will give you better performance, the only way to find out is to measure it on your platform. Measure, measure, measure. Okay, let's look at some sequence operation, which is a bit more interesting. What's commonly called filter is an algorithm that produces a sequence of elements that match a certain given predicate. So if I have a certain input sequence and I filter it, afterwards I have only, in this case, the even numbers. I have filtered out the odd numbers. In C++, the simplest way to do that is use the algorithm copyIf. CopyIf copies things. And sorry, I forgot the argument here. It's the output. Iterator should go there. And it will copy things only if the predicate, which will be invoked for each of the elements, returns true. If the predicate returns false, that current element will not be copied to the output. So just to give you an example, an input sequence, I just want to copy the elements that are larger than 10 in this case. And then the output will be obviously everything that is larger than 10. And here is the implementation of that copyIf, this time with the correct argument passed in. So we iterate over the sequence from first to last, and invoke the predicate for each of the for each element of the sequence, and only if that predicate returns true, we pass on that current element to the output. Fairly easy to understand. Again, you might say, hey, this is just a glorified for loop. Yes, it is. But you don't have to reason about the loop structure when you see in your code a simple copyIf. You know exactly what it's doing. You don't have to think in terms of loops. Even more, if you apply this algorithm on a data parallel architecture like GPUs, there might not be even a loop. They might do other things under the hood that don't even iterate over all elements. They might assign one processing unit to each input element and just do it in data parallel way, so that you use for 10,000 elements, you use 10,000 GPU cores, and in the end you will get what you want. That allows us to abstract ourselves from the sequentiality of the loop iteration I'm providing you with. I just provide you the implementation here to make it easier to understand what these algorithms actually do. Okay, so the question is copyIf parallelizable? We can invoke that function for each element, that's trivial. But where should that current element go in the output? What index should be used for a current element in the output? Remember, when we parallelize something, we take the input sequence, split the input sequence into pieces, and then apply the sequential version of that algorithm to the input pieces, to the chunks. That means that each of those chunks will produce an undefined number of elements, which in the end have to be concatenated. So each of those operations should put their result into the right spot in the output. So it has to know where things have to go. And that's a tricky part in parallelization of copyIf. You first have to find out where does the output for a particular chunk starts, at what index, before you actually can do things. So let's have a look at how we can do that. Well, I will give you just an example again. It's the same numbers as I had before. It consists out of several steps we have to perform in order to get a copyIf parallelized. First, we create an intermediate bit vector which tells us whether a current element is part of the output sequence or not. So you see those that are larger than 10 are part of the output sequence, and those all the others are not. Then we do a scan on the bit vector. Remember scan? Scan applies the given operation for each element. So essentially it sums up how many indices are being used for at this point. So that one uses one output spot. The 4 doesn't use one, so we are still at index 1. The 11 uses the next spot, so we are at index 2, and so on and so on. So you see, applying the scan operation on that bit vector already gives us the positions where things have to go, where each of the elements should go in your output, right? And last but not least, we can now use the parallel map to produce output, just by copying things into the output. We copy whenever the thing is 1, and only then. That's it. So we can parallelize copy if or a parallel filter by applying these 3 steps. And as it turns out, we can modify or specialize scan in a way that we don't need 3 steps. We actually can do the first part in the upsweep part of the scan algorithm and the copy part in the downsweep part of the algorithm, and we will get good performance out of it. So just as an example, we map by calling transform and create an intermediate vector of flags that will tell us whether a certain predicate is true or not. So after that step, the flags will contain 0 or 1, depending on whether the current element belongs to the output sequence or not. Then we do an inclusive scan over the flags, put the results into another vector. We just saw that. And last but not least, we apply a normal scatter operation. No, it's a scatter operation on the bit sum in the elements, which allows us to write things to the right spot in the output. Please note I have to subtract 1 here because our bit sum starts at 1. But the 1 should be the zeros element in our output, so I have to subtract 1 there. Any questions? Fairly straightforward. And you will, if you look at the implementation of copyif in the standard library, the parallel version of copyif, you will see something like that happening behind the scene, because it's the only way to get copyif implemented. But in parallel, I mean. Sequentially, it's not a problem, but in parallel, you have to jump through some hoops before you can do the actual copy operation. So as I said, the first 2 steps can be combined, and the last step can be done in the downsweep of the scan operation. So in the end, we end up with ON work, which is actually what you would expect, right? When you do a copyif, the complexity of that copyif should not be larger than the number of elements, obviously. Questions about that? Okay.
Sorry.
Yes.
So like, say it's busy chunks, and you do that function, scan the bit sum increment in each chunk. So like, do they share the current value of the bit sum?
The input value, the inputs, yeah, well, you have to, when you have an input sequence, you want to copy only part of the input sequence to the output. So you have to know where any input should go in the output. As long as you do that sequentially, it's not a problem, because you either copy the current element to the output or not. So the output will naturally increase as you need. But if you parallelize these operations, parallelization means you split your input sequence into pieces and run each of those pieces on a different core, because that's the only way to parallelize things, right? You have to somehow distribute the data across different cores in order to speed up things. So each of the cores gets only a subsequence of the input. From the 1st to the 5th element, from the 6th to the 10th element, the 11th to the 15th, and so on. But each of those subsequences still have to do a copy if. That means that each of the subsequences might produce less elements than their chunk sizes. Obviously, right? Because part of the things are not being copied. So this core runs the first chunk, this core runs the second chunk. Let's say we have 10 elements, 5 here, 5 here. The first one has to copy 2, the second one has to copy 3. Where should that core start copying its elements? Obviously in the third index, in the output. So you have to first find out where each chunk should start copying data before you can run it in parallel. Make sense? Other questions? Okay. There is a special case for scatter operations where you have indices that are not unique and you want to accumulate, for instance, things based on the index. You want to add up all elements that refer to the same index. And in this case, you need atomic operations because when you parallelize it and the index is not unique, you have to make sure that your accumulated result is not has no race condition. So you apply an atomic operation to do the scatter operation. So you take some input, or in this case, it's a gather operation. You take some input and you apply an atomic operation, and only the atomic operation writes it to the output. For instance, atomic add. So if you want to accumulate everything with the same index. How do you do that? Well, as before, let's assume we have some index sequence where the indices are non-unique. What I can do is sort the sequence of the indices according to the values in the index sequence. So again, I do a zip sort over the indices and the inputs, which reorders the input, obviously, so that I get the 3 index 0 first, then I get index 1, 2, 3. And that means that I have to start the accumulation at each bit that is set. So I have to sum up the 3 elements that come first, then I have to sum up these 2 elements, then I have to sum up that element. And this is a segmented scanning. That's what we talked about last time, right? So you can use a segmented scan to get exactly what you want, which will result in the application of our operator, of our atomic add, to the first 3, because this flag, if we use that flag as a beginner of a subsequence we want to scan over, which gives us the overall result in a nice way. So again, if you have non-unique indices and you want to apply a certain operation, make that operation atomic and use a normal segmented scan algorithm, and that gives you the result. Yet another example how you can use these building blocks to construct more complicated things on top of it. So an exercise for you. There are more sequence operations, obviously. One is called group by key, where you have an input sequence that contains all of pairs, the key and the value. And what you want to get out of it is a sequence of sequences, where each sequence contains all the values that belong to the same key. So the 1 has a 3, the 6, the 9, and the 2. The 2 has only 2 elements, 3, the 8, the 4, and the 8, and the 3 has only 1 element. So the exercises use your knowledge about data parallel algorithms to build an algorithm that does that. It's most likely a scan. So think about how you can apply these algorithms we talked about to achieve that result. Just grouping by key. Okay? There are more of those algorithms. Reduce by key, which is doing group by key, just that it additionally reduces the elements inside each of the sequences, adds them up or applies some reduction operation. So it produces a sequence of key and results. So it gets a reduction operation for the 1, for the 2, for the 3, and for the 4, and so on. And the other example is sort by key. which is the same as root by key, except that the sequences are ordered. Sounds like a zip, sort over a zip for me, to me. Just do a sort with a zip over the input sequence and apply a certain comparison operation, which makes sure that the output gives you exactly that. Should be straightforward. So please try doing it. It's a good exercise to get a feeling for how you can use these algorithms for your purposes. Questions? Okay. So just to sum it up, we talked about scan mostly. The parallel scan implementation is intuitively sequential, but we can find parallelism and we can implement it in a parallel way. And we know that the complexity is linear of that parallel operation. We showed that it's linear, which is good. But we also have seen that by creating hierarchies of these scan operations internally, we can utilize hardware capabilities in better ways by just deciding how many compute resources do I want to actually use for my algorithm. The segmented scan, one of the most powerful building blocks we have seen, that allows us to operate on irregular data structures, lists of lists, in a regular data parallel way, which is very powerful. Okay, so far for the list of algorithms I wanted to introduce you to. So let's start with a couple of examples. And I might not be able to do the second example, but at least one example I want to finish. Okay, so let's assume we have 1 million points, xy, that we want to sort in a grid-like way. We want to find out which of the grid cells has which of the points associated with it, or which of the grid cells contains which of the points. So in the end, we will come up with a list of lists where the outer list is a list of cells, 16, and the inner list is a list of points that belong to a particular cell. Okay? What I want to do is to derive or to show you 5 different ways how we can create that list of lists if we have 1 million points in hand and a grid structure. Where is that used? Well, that is a common operation in n-body problems, where you want to find all particles that are inside a certain distance from a given particle, so that we can reduce the amount of interaction between particles when we iterate, when we do the time step iteration over an n-body problem. Because each time step, in principle, requires us to look at the relationship between each of the pairs of particles, because we want to compute all the forces between each particle with any other particle, so that we understand what force is applied to a particular particle, so that we know in what direction it will fly in a galaxy simulation. So, for instance, we have a certain given particle, and we want to find all particles that are in a certain radius around that particle. And that if we have placed our particles in a cell, in a mesh, in a grid, we know that we only have to look in a certain subregion of that grid, so we can reduce the amount of interactive or interoperations between particles significantly, because we don't have to look into all the particles that are outside, in cells that are outside of that radius. So in n-body problems, as I said, the computer require pairwise forces between each pair of the points, and creating a mesh of points allows us to reduce the amount of required computation significantly, especially when you have a very large system like a galaxy you want to look at. You can ignore the forces of stars that are at the other end of the galaxy with regard to our own sun, right? So why do the computation if the impact of those stars that are far away are, well, you can ignore them essentially. Okay, so Question for you. How would you start working on this? How do you write that code? What I always suggest to students when they start writing code is they get a problem and they have an empty file where they start editing things. Okay, the main function is probably in there. Where do you start? Well, the first thing you always do when you start designing programs is to come up with the data structures you want to use in your code. And those data structures should represent the entities you are dealing with. So if you want to simulate particles, you probably want to have a data structure that somehow represents a particle. If you want to have a cell represented in your, or you want to deal with cells, you probably want to have a data structure that represents a cell, and so on and so on. So let's start with a very simple struct, which is we call point, representing one of those particles. What are the data members for a point? What properties does a point have? In a simple case.
Mass.
Yeah, for an n-body problem, you could have mass, yeah. But what else?
X, Y.
The coordinate, right? That's the one main thing you need, coordinates. There could be other things like mass or current forces or whatever is critical for your simulation. But the thing you absolutely need is a pair of coordinates. Okay, what else do we need? I already mentioned it. We need a cell. So a cell has probably its extent, the upper left and the lower right, which are represented by our point, and a vector of points where we want to store those points that are inside that cell, right? What else do we need? Oh, we have more than one cell. So we need a mesh. And the mesh again has a size. I need to know how many cells I have in X and Y direction. And I have a vector of cells where I store all those cells. So this are the data structures we want to work with. And as you see, it's fairly straightforward because all of them are actually vectors on the limit. So we know already that we can apply all our data parallel algorithms directly because it's vectors. I want to show you a helper function which we will use in all the code that follows, which is a function that takes a point in the mesh and returns the index into the vector of that mesh so that we know which index to use where to put the point essentially. And it just computes the position because it knows how many elements I have in X and Y direction, so it can just find out what is the linear index inside that vector for a particular point. You can follow the logic yourself. So just take away, this is a function which takes a point and a given mesh and returns the index into the vector of cells that point belongs to. That's it. Okay? So we have the basic data structures. Now let's do a sequential implementation because that is the first thing you always want to do. You want to implement it sequentially so that you have a good understanding of whether your algorithm actually works or not. So we create a mesh. The mesh is constructed based on its two extents. How many cells do I use in X and Y direction? And I want to time things, so this is what we have done before. No surprises there. And now what do we need to do? Our function receives the vector of points I want to associate with our mesh. Right? So we have to iterate over those points and call the function, this function for each of the points. And then use whatever it returns to refer to the corresponding cell and add the point to that cell. So it's fairly straightforward. So we want to go over all the points. We want to find the index. Where is that point? Which cell does that point belong to? And then we refer to that cell, which is in the mesh, use that index, and add the point to the end of that list. Nothing surprising there. So this is our sequential code. It will do what we want. At least I'm pretty sure it does work. Any questions so far? Okay. How would you parallelize it? Any ideas? what can I do to parallelize this algorithm? To associate all the points concurrently to their respective cells. Well, the easy solution is just, hey, let's parallelize that loop. Let's use a std for each and have a, just to show, we have a loop which we run in parallel. We compute the cell containing, we lock this cell, we append P to the current cell, and then we unlock it, because we have to take care of race conditions. Right? We have many threads doing the same thing, possibly appending points to the same cell, so we have to protect things from multi-threading issues. So how does that look like? Well, it's a for each over all points with a lambda which is called for each of the points. I find my cell index as before. I push my point back to the current cell, same as before, so the body is essentially unchanged. But what I need to do is to add some protection. I create a mutex, and whenever I want to push something back into my list, I lock my mutex to prevent multi-threading issues, which gives me a critical section that spans from the lock to the end of the body, which protects that operation. And that's a critical operation. Is that good parallelism or is that bad parallelism? I have a billion points here, or a billion points. And for each of the points, I have to acquire the lock. Will I get good performance? Probably not. So that's probably not what we want to do. And we have seen that in other examples before, that locking things just for every point in the input, for every element in the input, probably gives us very bad performance. What can we do about that? How would you go ahead and what would you change in order to make that more efficient? Well, what about if we have a mutex for each of the cells? So instead of having one mutex for the whole thing, we create one mutex for each of the cells, so that at least we can have concurrent operations with different cells at the same time. Okay. Do some kind of granularity, which is the same algorithm, just that we have a bunch of locks now, a bunch of mutices. And now, instead of locking the global mutex, we lock the one that corresponds to the current cell, and then append our P to that cell. So if we assume that we have a uniform distribution with 16 cells, for instance, 4 by 4, we get a contention which is 16 times less, right? Because we now can do more things at the same time, at least statistically. So what we need to add a mutex to our cell in order to achieve that. So in addition to the upper left and lower right and our list of points, we add a mutex to that data structure. And now we can change the algorithm we had before. Same thing as before, except that now we are locking the mutex that is in the current cell. So we find the index as before. We just take a reference of we find the cell we need because we don't want to write that more than once. Then we lock the mutex that is from that cell, and then we add the point to the list of points in that cell. Good enough? What do you think? Is that good parallelism? Can we do better? Well, I said I have 5 versions, so we will see that we can do much better than that. So the question is, how can we do that? Do you have any suggestions? How would you do that? Or would you parallelize things differently so that you can get more parallelism out of it? What we want to do, we want to avoid logging at all. We want to come up with an algorithm which prevents us from the need to grab a mutex. So we want to have an algorithm where each thread can do its own work without being hindered by the operation that has to be performed by another thread. Well, what we can do, we can create 16 meshes, and as many meshes as we have cores, and create partial meshes where each of the meshes can be accessed directly because one thread owns one mesh. And in the end, we combine the meshes into one and we get what we want, right? So we have a cell list. Now, for each of the cells and for each of the particles, we do the operation we need. So we go over all the cells in parallel. And for each of the cells, we go over all particles and associate the particles with a corresponding cell. And in the end, we combine the cells, the meshes into one, which is not shown. Okay. It's very inefficient, as you might expect, because we do 16 times more work than before, because each cell now goes through the list of all particles. So all threads go through the same list of particles over and over again. Even if they pick and choose only single elements out of the list, they have to go over all points because each of the cells has its own list of particles. But it might not run efficiently on thousands of GPU cores. So you might want to have, the parallelism is limited by the number of cells you have in your meshes, essentially. So if you have only 16 cells, then you can run not more than 16 cores or 16 threads. But let's have a look at it anyway. We have seen all the constructs we need for that before. This time, the outer loop goes over all the cells and will invoke the body for each of the cells as before. And that happens in parallel. What's inside? Inside is essentially our sequential algorithm. We have to invoke for all the particles. So nothing surprising there. We go over all the points, and for each of the points, we do find the cell index, and if the cell index corresponds to the index of the current cell, we push it back into our list of points. Where's the data parallelism, you might ask? I got carried away by using the for each here over and over again. But after I wrote that code, I said, wow, we can do better. What can we do instead of the inner for each? What operation can we apply? We talked about that just earlier today. What is that inner operation essentially? Oh, it's a filter. We want to copy only those points that correspond to a certain criteria. So let's change that into a filter operation. It's just a copy if over all our points, and if the condition is the index is equal to the find cell index of the current point. And only then things will be copied to the output. Otherwise it will not copy things. So you see that often you might tend to write a for loop, but you're actually re-implementing something that is existing in your toolbox. So always think twice and try to understand what is it actually I'm doing. And if you write copy if, it's much more readable than the code on the previous slide, which has a for loop, which is kind of doing weird things. And you have to first understand what the inner loop does. Whereas when you see this code, you immediately see, yeah, okay, it's a filter, it's a copy if. So it allows you to reason about things much better if you use abstractions that are primitive. Okay. What else can we do? Well, one thing we can do, as I said, we can have partial results and combine them. Because now we don't need to synchronize at all. We need to create each of those subcells separately, and in the end, merge them together. And for that, we have all the tools available as well, because we introduced the reduction operation you can apply to the HPX for loop, where you, which does exactly that for you. You tell it, please reduce over M over my mesh using that special function, which I called combine meshes. And then it will invoke each of those functions with a thread local version of the mesh. So it will duplicate the mesh triplicate the mesh underneath, will create as many meshes as you need in terms of cores, and will invoke the body on a thread local version of the mesh, which avoids for us to have to deal with multi-threading issues. So the code is absolutely the same as we had before. The for loop, when you give it a reduction, will invoke that combine meshes function in the end, which will combine all the meshes which we have filled while executing over our points. And to show you what that combined meshes does, it receives an accumulated version. So essentially, you can think of it as a function you're passing to reduce. It receives a version where you want to accumulate things, and the current instance that has to be added to the accumulator. Again, I got carried away. I just wrote a loop which is doing that. It goes over all cells, and for each of the cells, it combines the points which are in the two cells. And then I said, hold on, that doesn't look right. So I stepped back and said, okay, why don't we just do a zip and implement a normal gather operation, which we talked about. And now you get exactly what you need. So you zip over the cell, the accumulated cells and the cells from the current element, and simply copy the elements from the current element, the points from the current element into the points of the accumulator. Done. So it's, again, much easier to read than what we had on the previous slide. This requires really some attention to figure out what the hell is it doing. Whereas that version doesn't require anything. It's just obvious what it's doing. Right? It goes over all the cell combination of cells and copies things over. Straightforward code. So always try to write code with a higher level abstraction that allows you to reason about the code afterwards. Okay. Any questions? I still have a fifth version, and then I will show you the measurements. So we should be fine time-wise. Let's do a data parallel approach. Because so far we haven't done data parallel stuff. We haven't applied our algorithms too much. So what can we do? Just schematically. What we could do, we could compute the cell containing for each particle using a transforms, using a map. Just go over the list of particles and figure out what cell index does that particle belong to. So the first one belongs into index 9, 6, 6, 4, 6, 4. So that's these points you see on the average. So that's the first thing. Simple parallel map over the points. Then you sort the results by the cell. Again, it's a zip sort, which sorts over the cells, right? So it puts together the cells that belong to the same index, and it corrects the particle index, obviously, because you sort over the zip. And then you use that information to build the start and end indices for the particular cells. Right? This starts at 0, that one starts at 2, that one starts at 5, and has one element. So again, just by applying these simple, straightforward steps we talked about, namely the transform and the sort, you can get to the result where you want to be. You know which cell should contain which of those pairs of things. That cell should contain 0 and 1, so particle index 3 and 5. Cell 6 should contain 2, 3, and 4, which is particle 1, 2, and 4, and so on. So let's look at some code. As I said, the transform. And the transform just invokes the find cell index. We want to find all the cell indices for all the points. And then we do a zip sort over the points and the indices, where we order things based on the indices, as I said. Right? The one refers to the element that comes, it's the second element to the zip. And last but not least, we apply a bit of magic to find the things we have to copy into certain cells. this is really technicalities, has nothing to do with data parallelism. I wanted to show it anyway, so please go back to the code if you want to have details. Just for brevity reasons, I'm not going to explain it. But what I want to do is to give you timings. What I did is I ran all the 6 versions, the sequential and the 5 parallel version of the algorithm on 4 different meshes. 4 by 4 elements, 32 by 32 cells. Now, let's have a look at the numbers. As you can see, interestingly enough, the sequential version gets slower and slower the more meshes we have. Any idea why that's the case? Still the same number of points I'm associating with cells, but the time actually is almost 3 times as large when I increase the number of cells. What's the reason? Well, say memory, that you're fine, right? Just say memory. It's always correct. Caching, locality, which holds. So as you see, it gets slower. If you look at the parallel versions, we see that the 3rd version is actually the fastest for a very small number of cells. But if you increase the number of cells in a mesh, the 5th version, the data parallel version, gets the fastest one. And interesting enough, the data parallel version doesn't get much slower when you increase the number of cells underneath. Which is actually an important insight, right? So the sequential version goes up, but the parallel version stays roughly the same in time, no matter how many cells you have. And it's much, much faster than all of the other versions. So even if you might have thought, hey, I'm doing 3 loops, one after another, I have to do a lot of computation. As you can see that data parallel algorithms might be much, much more efficient than any other algorithm you might come up by hand, written by hand. And by the way, needless to say, the one with the single mutex is just awful. We knew that before. No surprises. Okay. What's the conclusion? The conclusion is you don't know which algorithm will run fastest. You just don't know that. Because it depends on your machine you're running things on. It depends on the architecture you're running it on. Is it a GPU? Is it a CPU? Is it an ARM architecture? And so on and so on. So the only way to figure out what algorithm is best is to do the 3 things I mentioned before. Measure, measure, and measure. And only then you will know which of the algorithms you should actually use for your particular application to get best possible performance. Okay. At that point, I'll shut up. Thank you for your attention. Yes?
Is it the reason why version 2 gets better with size?
Sorry?
Is there a specific reason why version 2, the V2 gets better as you increase the size?
Because you have less mutices, right? You have 1 mutex per cell, and you have 16 mutices, and here you have 1024 mutices. So you have a lot less contention. The probability that 2 threads want to grab the same mutex is much smaller here than here, right? So that's why it's getting faster. Good observation, yes. Good point. Other questions? No? Well, thank you so much. See you next week.